according to the lab manual that has been sent to you. So not that what have been shown in our lab experiments, that you have to write. All the things that have been shown in this in previous labs, lab 1 and lab 2, those things you need to write. Okay, am I audible?
Yes, ma'am.
Yes, ma'am.
Yes, ma'am.
Those things you need to write. So and submit that accordingly. আমাকে কেউ WhatsApp করেছিল, but I actually avoid replying in WhatsApp, so that's why I am telling it now. Okay, I think most of you have joined, so let's start. So actually up to this point we have been considering the semiconductors and their various properties, like firstly we consider the intrinsic material, whereby only the current or the charge carriers are only intrinsic, that is the property which is strictly related to the property of the material itself. Henceforth we considered some extrinsic semiconductors where we actually try to increase the conductivity by inserting dopant levels or dopant atoms. In the P region, we have been we have doped it with acceptor ions or the trivalent atoms specifically, which makes proliferation of holes on the P side, and in the N side what we have with is we have been doping with pentavalent impurity atoms, which has nothing but leave an extra or leave an excess of electrons, and thereby the majority carriers in the N side is the electrons itself. So what we are left out is that in the P side we have majority carriers as holes and minority carriers as the electrons, as because electrons are much fewer in number compared to the holes. So here holes play a dominant role if it is given a proper bias in carrying the current. But still in the total current contribution, the minority carrier electrons on the p-type semiconductor also plays a significant role. That we'll be studying later, how this how the current carried by some device is being controlled by these minority carriers through that, also because that also contribute to some current, which is basically the reverse saturation current, which will be covering in probably in future couple of classes. And on the inside also, the majority carriers are electrons and the minority carriers are holes, for the same reason as has been said. And this up to this points we aware with this kind of things. Also we are able to determine the positions of each of these intrinsic semiconductors as well as these extrinsic semiconductors, p-type and n-type. Now we are trying to create a situation whether we can make something interesting by having some things organized onto it. That means the first thing that comes to our mind is probably if we can join these two distinct or two individual p-type and n-type semiconductor and make them in contact. So basically, if we are now trying to make something fruitful, if we are trying to make something some device or design a device the first thing that any device would have is at least consisting of one junction. And now we'll be considering this one PN junction. So the first point to note is that we let a p-type semiconductor and an n-type semiconductor and join them. Actually, this is not the practice how this PN junction is formed. PN junction is formed in some another technique. There are several techniques, but this is very colloquial to say that joining a p-type and n-type and then forming a contact, then forming one metallurgical junction. So this is not that will be a really bad PN junction if we are going through that way. But normally, that what is done is that we take a single crystal, we dope one side with the P or with the acceptor impurities, so that there are excess amount of holes there, and we dope another side. Is the screen black for also? Yes, I have still not started anything to present, so that is black. Okay, so one side is doped with acceptor impurity atoms, and another side is doped with dopant impurity atoms. So that is the scenario how a PN junction is formed. And it is tried to make this junction abrupt as far as possible, because henceforth in all our calculations we will be considering that on the left, we'll be considering that on the left plane, if we are doping with p-type materials, or if we are doping with the acceptor materials, then the p then this p that means the number of holes that reduces abruptly to zero at the junction itself. And the n-type, and in case of n-type semiconductor also, that means on the other half of the crystal of the semiconductor, which is basically now the n-type, that also reduces to zero abruptly at the metallurgical junction. So these are the two considerations that we'll be taking into account in our further discussions. So now let us try to draw a PN junction. Just let me check, my device is not actually working. I think it's out of charge now. Just spare me a second. Just spare me a second. Is it visible now? Is it visible now? My can you see whether I am writing?
Ma'am, yes, ma'am.
So let us try to draw a p-n junction. So what I was actually saying is that if this is your P side and this is your N side, and what we are going to have is that on the P side, we have been doping with effector impurity atoms, so there will be excess of holes. Let us draw that quickly. So what is the problem? What's the problem occurring actually? So, so this is the P side where we have been doping with and there are holes associated with each of these atoms, ions. So now we are considering this material at T is equal to 0 K. Let us first consider these two things are not joined. Basically, so this problem is occurring. It is a distinct region. This P region is a distinct region, and N region is also distinct. They are still not joined. So what are their expected energy levels? So if we can express it in terms of energy band diagrams, what it should look like. So this is the conduction band, EC. This is EV. Here also, this is EC, EV. And now at T is equal to 0 K, what is expected to happen? Yes.
Ma'am, no excitation, so everything should be in valence band.
I can't listen you actually, your voice is rather. Yes? What is expected? Nothing expected, actually. Nothing is expected. Just the values, the acceptor level, that is EA, should be just above the valence band level. And here also, in case of the inside also, the donor level is sitting over here, the ionized atoms are sitting over there, nothing is going to happen. And as a result of it, what is the Fermi level? It's what is
So mid gap.
What?
Midway between AC and
Yes, just middle of the band gap. So EF is just at the middle of the EI is equals to EF. So the of both of these things, of both of this p type as well as at the n type, the Fermi level is just at the middle because all the electrons or the holes are attached with their associated atoms. They are not free yet. So the probability of finding them is exactly half. So so basically nothing is going to happen. Now, if we now join these two, let us suppose there is only one line, which means that now the P and N, I think there is some problem with this drawing. So if now P and N are joined, what is expected? At T is equal to 0K. So nothing as such much difference is expected, only that the P and N, which were distinct apart, now as they come in contact, they must act as a system, and all the energy levels, or at least the Fermi energy level, must line up to indicate that this system is now in equilibrium, thermal equilibrium. So the Fermi levels must line up, and nothing exciting that basically happens to this. Now, if we are considering a scenario where we are having T greater than 0K. Now we are having T greater than 0K. T greater than 0K, then what is expected? But still lesser, T greater than 0K, but still less than T room temperature. Now, some of the holes, if you can write, if you can draw that again, acceptor ions associated with a hole, acceptor ion associated with a hole, acceptor ion associated with a hole, and in this side, the donor ions associated with an electron, the donor ions associated with an electron. Here also, we are completing the drawing. Now, what happens? This hole will try to move on, will have some thermal energy associated with it, because we are now have increased the temperature above 0K. So now these holes on the P side and these electrons on the N side will have some thermal velocity, and they have started moving randomly in several directions, and they go up ending in that direction where there is a greater probability for recombination with the holes. Up to this point, it is clear. These electrons are moving randomly throughout the entire crystal, and they end up moving in such direction where it finds a hole nearby. So there is nothing such very magical things happening over here. In many of the books, it is written that there is a lack of holes on the inside, so it goes onto the P side and sees a hole thereby. There is nothing very magical about it, because this is the scenario of a hole and electron, because they have to recombine ultimately after some period of time. So they basically end up on the other side where is a greater chances of recombination. Similarly is the case of holes moving thereby on some part or some region where it finds there are innumerable number of holes, or sorry, electrons, where they could recombine, they could go and recombine that place. But what the important thing that occurs over here is that when this happens, when an electron goes or crosses the junction over to that side and recombines with a hole, similarly, when a hole moves to this side and recombines with, and say if this is also also a recombination process. Either of these two processes is recombination because this annihilates electron hole pairs. So if this is recombination, if going on the either side leads to the destruction of this electron hole pairs, then what we are left with is that we are left with some uncovered ions or the uncovered static charges, which are nothing but this donor impurity ions on the inside and acceptor impurity ions. Sorry, these are now ions because they are not having their associated extra hole or the extra electron with them. So now these have been converted into ions. So these are now ions basically. This acceptor atom, which has an extra hole a few minutes before, now has a lack of hole and it has become an acceptor ion. Similarly, here also, this donor atom, which has its associated electron with it, now has a lack of electron, that extra electron. It releases that electron and becomes an ion. Thus, these uncovered charges, thus as this electrons and holes cross through this junction, this is the junction, or say metallurgical junction. If this is your metallurgical junction and where there is a higher chances of or the higher chances of the higher probability of the recombination, their fate is actually to recombine at those places where there are higher chances of recombination. So basically at this junction, what we are left with is that there are few uncovered donor ions on the inside and acceptor ions on the p side. So now my question is that while crossing these holes on the inside, electrons on the p side, if this process carries on like this, as they are moving, more and more uncovered charges are left with. So is this process going on continuously?
No, ma'am.
So why?
Ma'am, a potential barrier is created at the junction, which opposes the flow of the carriers.
Yes, potential barrier is formed as you see that these are immobile ions that are deep down, and they are basically immobile, that these ions. So these ions form these are the positive sides and these are the negative sides. If you can think it of like this, then the electric field, there is a generation of electric field in this direction. Do you agree with me? As these are uncovered charges and also they cannot move compared to their counterparts, that is holes and the electrons. These are sort of standing there, deep down there, tight down there. So they basically contribute to the electric field at the junction. Now, whether this electric field facilitates the flow of electrons towards this site, let us examine that. So now, at the metallurgical junction, what we had earlier is that at 0K, nothing is happening, nothing is ionized. And we say that when PN junction is formed and yes?
Ma'am, what will be the direction of electric field?
From positive to negative?
Yes, ma'am, that's obvious. But ma'am, it would be, ma'am, left to right, ma'am.
What?
The direction of electric field would be from P to N in the barrier.
So your voice is not audible.
Hello, ma'am.
Hello.
Hello. Yes, ma'am. Am I
Hello.
audible?
Yes. 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 Yes.
Yes, ma'am. The direction of electric field will be from P to N, ma'am.
Why?
Because if the direction of the electric field will be from P to N, then the electron that are going to be from jumping from P to N will be get repelled by the electric field. Means will be experiencing force. So that will stop the flow of electron, and that is why the barrier potential is being created.
No, no. Actually, I am talking about the barrier potential at the junction itself. Look, this electric field is. Hello. Am I audible?
Yeah, yes, ma'am. Yes, ma'am.
Yes,
So
ma'am.
this is the barrier potential that has been generated at the junction itself, because these are uncovered charges, and rest of this thing is neutral. As we have already mentioned, in a bulk p type or the bulk n type, this is, you can say this is bulk, because there are total number of holes that are associated, the total number of electrons, extra electrons exactly balances its it's imputed that is positive charge exactly balances with a negative charge. So on the bulk side, the electric field is zero. But what this happens, this is not neutral. Mind that this is not neutral, because now they are lack with their associated atoms, associated carriers. These lack actually their holes, and this lack their electrons. So contrary to this portion and this portion, which is basically neutral, this is not neutral, because now there are excess of positively charged ions over here, and excess negatively charged ions over here. Do you agree with me? The bulk
Yes, ma'am. Yes,
side
ma'am.
is the bulk side is rather neutral, because this extra electronic charge is this whole charge is exactly balanced by the negative acceptor ion charge. So that should be neutral, because they are equally in numbers, because these holes are being generated from this excess the excess acceptor ions that is responsible for its creation. Yes. And this side also to holds this logic, because of the same thing, because this extra electronic charge is equal to its associated parent atom. So this particular region, which are left with uncovered ions, this generates an electric field. Now if we can draw this profile in terms of the energy band diagram, what is expected? So the first thing is that when it is to work as a system, the Fermi energy level must line up. So it is true, the Fermi energy level must line up. So let us draw a constant Fermi energy level, which is now E of F. So this is E of F. And in the P side, this is C, and this is your EV. Similarly, this is at the P side, and this is the metallurgical junction. This is your this is your so this region has specific names. Let me call it out now. This is devoid of any charge mobile carriers, that means it lacks electrons or holes. Likewise, what we call as mobile carriers. So this is known as depletion region, because again someone likes to join. So again, this region is known as depleted of or depletion layer. This is also known as depletion layer, as because this is depleted of any mobile charge carriers. So another name is space charge region, because it has a lot of such space charge or uncovered ions that is sitting over in this depletion region. So this is also known as space charge region. So there are several names to this region, because that particularly a very important property of any p-n junction diode. So this is that. So let me draw this. So this is this edge, this is this edge, and this is this edge. So here, this is the extreme length to which the junction, to which this space-shared region extends up to in the p side, and this is this region where the space-shared region extends on the n side. So now we can comply with our previous discussion and the energy band diagram that has been drawn in relation to that. And this is the intrinsic energy level, which is basically at the middle of the band gap. This is EC, this is EV. Yes, intrinsic level basically tells how much intrinsic carriers are present, and that particularly is sitting at the middle of the. Note that while drawing this energy band diagram, EI should be at the middle of this EC and EV, and the Fermi level must be a constant throughout this system, as because to indicate that this system is working under thermal equilibrium. So nothing more and nothing less is there, so that particularly in total coincidence with the thermal equilibrium process. So this is this. So EF is aligned for both the P region and the N region. So EF is aligned for both these two regions. Now, what is this? So we were just talking about E. So is this E facilitating this process of flow? That means crossing of the holes towards the N region and crossing of electrons towards this P region. Is this E, that is the electric field generated in this region, facilitating this process?
No, ma'am.
No, because in the conduction, in the N side there are electrons. In the conduction band, that is expected, and electrons see an uphill here. That means there is some potential barrier that is developed. So this electric field tells that no, please go back, please go back. Tells electrons to go back, please, to your side, to your own side. And here also, in these holes also, these are the holes sitting over here in the valence band for the p-type for the p-type region or the p region. So this is also upfield for the holes, so it cannot cross the junction and come into the p side. Come over this barrier potential to cross over to the p side. This is also uphill for the holes.
Ma'am, one question.
Yes.
Ma'am, this Fermi level is constant. This is depicting thermal equilibrium.
Yes.
Okay.
What we have actually, if you can remember the Fermi-Dirac distribution for holes, this is actually upside down. If we are drawing this energy band diagram for electrons, okay, for holes, it is just reverse. Yes, you can remember that 1 minus FFE. So it is just reverse. So if we can draw the energy band diagram for the holes, then also we will see that this is actually uphill for the holes also. In contrary to this, where it is seen that yes, no, it's downhill. Actually, it's not downhill. It should be uphill, because we have drawn this energy band diagrams in terms of electrons. So if it had been drawn in terms of holes, then it would be an uphill also. Okay. So what I'm trying to actually explain is that in both of these cases, maybe it for holes on the p side and maybe it for electrons on the n side, both of these experiences, what is called the potential barrier is being developed, that basically hinders from their crossing to the junction and going to the other side. So we can also draw that Maxwell's Boltzmann distribution, which is absolutely applicable at higher temperatures. And if that is that, then some of the electrons which are residing here, only this can pass through this direction, that is pass through this direction to the p side by crossing the junction, and the electrons that are sitting over here just bounce back. Here also, if you can draw this one, then only the holes residing here can cross, and the holes sitting over there just bounce back. This electrons bounces back to their own side. So what we are left with, this electric field basically hinders the further flow of electrons to the p side and further flow of electrons, holes on the p side. But mind that in this electric field basically facilitates the flow of minority charged carriers. Isn't that? The flow of minority charged carriers,
Yes, ma'am.
which we'll be discussing probably in the later classes also, what are these minority charge carriers, and we also take into account these minority charge carriers for the generation of the diode current and all that. Those things will be included onto that. But before that, what we'll be explicitly talking about now, will be dealing mainly with the majority carriers, and that typically entails that when such electric potential is being developed at the junction on account of this immobile ions that are sitting right at the junction, the charge carriers are bounced back to their own side. So in this discussion, we will not go further, because now we will say that this enough of electric field has been developed, which now further hinders the process or the flow of the diffusion that is being or the diffusion that is being. So can you say that whether this is drift or that is diffusion, the process that has been described here, that is the movement of the holes, movement of the electrons on either side of the junction, whether it is holes or electrons?
Drift.
What is that?
The majority charge carriers.
Now, no, I'm saying what is this process called, whether it's drift or diffusion?
Diffusion.
Yes, this is diffusion. I actively stayed out from this discussion, that is diffusion, because it is such a simple phenomena, that is, it is such a very known or very common phenomena, and this is being done only owing to this thermal process, to this thermally generated velocity of that is being imparted onto this carriers, and they are crossing the junction on account of this. So this is basically up to this is only the diffusion of the electrons. Now from this point, we'll be trying to calculate how much this depletion region width. Now we can say that there has been a depletion region that is extending to the p region. Some of it is extended to the p region, some of it is extended to the n region. So there is some width that is being generated. Now we can calculate this width basically based on the barrier potential, that is VBI, that is being generated, and for that calculation we need how much charge that is present at this depletion region, and all that. Those calculations will go hand in hand to finally calculate the electric field that is being generated at this depletion region. So going with this picture, so this is EI, that is the intrinsic Fermi level, EFI. I can designate it as EFI, and this here also it is the EFI. I think I should draw that in a separate page. So this is your P side. And this is a depletion region. And this is the constant Fermi level, E, F, on both of the sides, and this is EV, this is EC, EC, and this is just at the middle, that is EI. Now, the intrinsic Fermi level is equidistant from the conduction band edge. So, typically, we are considering this is the conduction band edge. This is the conduction. So, this should not happen because we have drawn the edge of the semiconductor up to this point. So, this should not be there, though it is difficult for me to rub at this point. This should be this, and this should be this. Okay. So, we will not be having these lines over here. So, okay. The intrinsic Fermi level is equidistant from the conduction band edge, that is EC, and what we are considering is a conduction band lies above this EC and the valence band, and the rest of the energy levels in the valence band lies below EV. So these are typically the edges of the valence band, and this is to the conduction band. So the potential, the built-in potential barrier is what is that? This built-in potential barrier, or VBI, if this has been developed on account of this immobile ions, then what is expected? The change in this VBI, or the potential that is being generated over in this region must be generated at must be depicted in this shift in the energy level. This shift accounts for this. So this is typically the VBI, or if written in terms of energy levels, then E into VBI or Q into VBI. So we can calculate this VBI. Now we know this if we have the values for these two energy levels, that is EF. So EFI, this is EFI minus EF is equals to E phi FP and EF minus EFI is nothing but E phi N. So VBI, which is nothing but phi F P plus phi Fn, this VBI can be calculated. We know at the P side, at the N side, the electron concentration in the conduction band can be given by N0. So writing it over here, N0 is equals to Ni exp EF minus EFI divided by KT. That is that. On the N side, the number of electrons, the electron concentration in the conduction band is this. And on the P side, the whole concentration can be given by the similar expressions. P0 is equal to Ni exp EFI minus EF by KT.
Then what is VBI?
VBI is the barrier potential.
Okay, ma'am.
there has been an electric field that is generated over here, and because of that there is a barrier potential. Okay,
Yes, ma'am.
that
Yes, ma'am.
this barrier potential hinders, the further crossing of electrons on this side and holes on this side. Okay, so this is the
Yes, that
potential
was like I was just asking.
that an electron faces, and a hole faces on crossing to the either side of the junction. So that is barrier potential.
Yes,
So
ma'am.
in calculating this, what we are left with now, we can just put the values over here, that is E of Fi. So for P0, what we have, P0 is nothing but Ni Exp EFI minus EFI minus EF. So it is on the P side. So we can just put it over here, E phi FP divided by KT. Now we can, what we are trying to get out of this is this phi F. So to calculate the VBI, so taking log on both sides, ln P0 by Ni is E phi F by KT, and we have phi FP is equal to KT by E ln P0 by Ni. So phi FP is that, and for if we can take out phi Fn, then from this expression at the end side, what we are left with is N0, just putting the value of EF minus EFI and then writing it over here. So I think it was EFI minus EF. So nobody corrected me. So this is EFI minus EF is equal to E of F phi n. So Ni is equal to EXP, because EFI is at a higher energy level corresponding to EF. So at the P side, at the N side, what is happening? EF. So EXP, EF minus EFI, which is nothing but EXP minus of E phi n divided by KT, which is phi of Fn is equal to, this minus gets over here, KT by E ln N0 by Ni. So for larger doping concentration, so if N0 is nearly equals to the donor ion concentration, then what we are left with is that N0 is replaced by ND and P0 is replaced by PA. So this is that. Now we can calculate VBI having considered that we have calculated E phi of Fn and phi of Fp. What we are left with? Phi of Fn plus phi of Fp, that is equals to VBI. So VBI is equals to KT by K, that is common, and ln Na Nd divided by Ni square. This is nothing but voltage dependent on temperature, Vt. So this is this. This is the thermal voltage, and any of the such kinds of equations that is involving KT and all that, you will absolutely consider that this is a thermal device. Okay, where there is some equations, the current derivations, the voltages that has this KT by E or by any term involving KT. So these are thermal devices. Now, this is the equation for the barrier potential. Now, what is the takeaway from this equation? What is the takeaway from this equation? This equation just a significance of what we are trying to tell in language, but so that language is basically important. So what is that? Yes, what does this equation tells us? Yes, anybody? Are you listening? So I can't listen you. Yes, you get my point?
Yes, ma'am.
So what have I asked actually? Did you went to sleep? Or
No, ma'am. There is a network problem, I guess. Like, my Wi-Fi is disconnected, so I connected through my normal data, so I couldn't listen you.
so what about others who are present in this class? So what is the takeaway from this equation? So let me ask you this question. What is the takeaway? Because we can see here that there is some dependence of this VBI, that is this voltage, or the thermal voltage, or the built-in potential voltage, is being dependent on several factors, isn't that?
Yes, ma'am.
Na Nd divided by Ni square. That means it has a logarithmic dependence with this typical, because K, T, E, Ni, these are all constants. But what we can vary is this Na and Nd. When we typically start, we typically start off with the material, then the intrinsic concentration is probably probably constant. But what we are left with is this Na and Nd, which are variable. So if we increase this doping concentrations, then what is expected?
The barrier potential increases.
No, the barrier potential reduces because it has a logarithmic
The
dependence on,
Ni.
yes, Na and Nd, because it has a logarithmic dependence on Na and Ni. In Na and Nd. So can I give you a problem?
Okay, ma'am.
Calculate the built-in potential barrier in a p-type PN junction. Yes, given a silicon PN junction at
Repeat again, please.
calculate the built-in potential barrier for a PN junction at T is equal to 300 K with doping densities Na is equal to 1 into 10 to the power 18 per cubic centimeter and Nd is equal to 1 into 10 to the power 15 per cubic centimeter.
Please repeat doping concentrations.
Doping densities at Na is equal to 1 into 10 to the power 8 per cubic centimeter and Nd is equal to 1 into 10 to the power 15 per cubic centimeter. Assume Ni is equal to 1.5 into 10 to the power 10 per cubic centimeter.
What was the temperature?
Temperature is equal to 300 K
Okay.
and Ni is equal to 1.5 into 10 to the power 10 per cubic centimeter.
Then Na is 1 into 10 to the power 8. Am I right?
Na is 1 into 10 to the power 18 per cubic centimeter.
Okay.
What is the built-in potential barrier?
And 0.7542.
Yes. Now, if we change this accepted doping concentration from 1 into 10 to the power 18 per cubic centimeter to Na is equal to 1 into 10 to the power 16 per cubic centimeter. Nd is kept constant to 10 to the power 15 per cubic centimeter. Only the Na is changed to 10 to the power 16. What is the built-in potential barrier voltage?
No, 1.25.
No?
0.635.
Yes, 0.635. 0.65 what? Volt. Yes, unit is volt because we are calculating the potential barrier voltage, barrier in terms of voltage. So you can see here that changing the concentration from 10 to the power 18 to 10 to the power 16, this barrier potential is reduced. Okay. Now, what is its connection? If a thing is heavily doped, say a thing is heavily doped, then what is its consequence?
The barrier potential increases.
Decrease.
Okay. Now we will henceforth move to the and what about the barrier width? Is the barrier width will also increase with the increase in this doping concentration? or else reverse?
It
It's
will
reverse,
decrease.
ma'am.
It will decrease.
Decrease.
Why?
Ma'am, for getting the same potential difference, ma'am, we will need to, ma'am, ma'am, V equals to EDL. Ma'am, there, ma'am, for getting the same potential difference, if E is getting increased, ma'am, we will require a.
Somojit, your voice is actually breaking. I can't listen you properly.
ম্যাম বলছিলাম V equals to EDL.
হ্যাঁ,
ম্যাম ওখান থেকে ম্যাম সেম পোটেনশিয়াল ডিফারেন্সটা পাওয়ার জন্য ম্যাম ইটা যখন মানে কনসেন্ট্রেশন যখন বাড়াচ্ছে আমার ইটা তখন বেড়ে যাচ্ছে, ওর জন্য ম্যাম ডিএলটা কম হয়ে যাবে লেন্থটা।
একদম rightly said. Rightly said, and it's true that if we can increase the doping concentration, that means we now have a larger number of impurities or larger number of carriers per unit volume. So if we are going to calculate this, how much depth the depletion width will extend up to the P region or to the end region, that completely depends on this number of this. That also depends on this number of carrier concentrations. As because with this increased carrier concentration, what happens is that within a small volume, what we expect is that now there is a larger concentration of different dopant atoms or different acceptor impurities. Various dopant atoms are like acceptors and donors. So that particular electric voltage that will basically restrict the flow of the electrons causing to the either junction can be reached at a very with a small amount of depletion region width to basically balance out this process of diffusion on either side of the junction. আমরা যত diffusion যত বাড়াচ্ছি, তার মানে কি আমরা পার ইউনিট ভলিউমে এক্সপেক্ট করছি বেশি নাম্বার অফ চার্জ ক্যারিয়ার্স। তাই যদি হয় তাহলে পরে যে নাম্বার যতটা ভলিউম অফ আমাদের ডিপ্লিশন রিজিয়ন উইথ বা ইলেকট্রিক ফিল্ড বা পোটেনশিয়াল ব্যারিয়ার যতটা লাগছিল ফর এ ওয়াইডার উইথ, সেটা এখন কম লাগবে, কারণ ওই স্মল রিজিয়নের মধ্যেই আমি তত অ্যামাউন্ট অফ চার্জেস পেয়ে গেছি এদের দুজনকে কাউন্টার করার জন্য, তাই তো? ডু ইউ এগ্রি উইথ মি?
Yes, ma'am.
Yes? Do you agree? Okay. So depletion region is expected to decrease if we have a larger impurity concentration on those side, and that particularly increases on that side where there is a larger doping concentration. It may so happen that on the P side and on the N side there are different amount of concentrations that are happening over there. So on the lesser side, the depletion region will extend onto that side. So that is the scenario. So now we are going to calculate it. Once we have calculated this barrier voltage, we can now calculate the electric field. For that, we would need the profile of the charged carriers that are present, or the charged ions that are present in that stress charge region, and based on that we'll be integrating that to find the electric field. Again, we will be integrating electric field to find the profile for the barrier potential. So let's go on calculating that. So I'll try to draw that again. So the depletion region extends to minus of xp. So the depletion region starts. This is a metallurgical junction from which the depletion region starts to increase at the p side, which has its maximum value. Which has its value at x is equal to minus xp, and to xn plus of xn at this end site. So yes, now an electric field is created, as it has been said earlier, in the depletion region due to the separation of this negatively charged acceptor ions and positively charged donor ions in this very depletion region. The volume charge density distribution in this depletion region can have a profile like this. Let us draw that. I think there is some problem with this. Plus on this side and a minus on this side. And what is, if we consider it as uniform doping and an exact abrupt junction approximation, which means that on the p side there is an abrupt change in the nature of the charge density, which that basically means that the minus is changed to plus just crossing this junction. So this is abrupt junction approximation. There is also graded linear junction approximation. There are various approximations onto it. So this is basically my charge profile. That means here on this side, what is this? So what is this charge volume? E times ND. Yes?
And what is XP and XN?
Xn means xp is the distance up to which this depletion region penetrates onto the p side. If 0 is our axis, and on the p side, if this region extends, we have designated as minus x-axis, and if it penetrates onto the n side up to xn, then xn is probably the maximum distance at a particular voltage that is obtained, after which this depletion region which penetrates on the inside. So this is the
XP and XN won't be the same.
Yes, xp and xn would be the same if we are starting with the same amount of charge distribution or the same doping amount. That means Na and Nd is equal. If not that, if this is not the case, then probably there will some difference in xp and xn, and henceforth all the calculations will be different. That means all the profiles, the curves that will be drawn hereafter will be different. If there is some difference in Na and Nd, henceforth there will be, as has been told earlier, xp and xn will have different values if we have different doping concentrations at the p side from the along with the different doping concentrations in the inside. Up to this time, we have considered that they are doped in same amounts. Okay. Is it clear? Okay. So my drawing might be something that is misguiding to you, might seem misguiding, but that is not a scenario, because I have once I am drawn this rectangle, I loses control. But why this is happening today, I don't know. So this is the problem that is actually facing. This is basically E into Nd, the total amount of charge times the number of the ionized impurity atoms, and this is probably E times, so that is minus E times Nd, because in this case here we are having a negatively charged acceptor impurity atoms. So minus E of Nd. So up to this point this is clear. So minus of xp, so this is minus xp, and this is plus of xn, as we have noted in our convention in this diagram also. So this is plus of E of Nd, which is the charge density, at the n site up to xn, and the charge density that is minus E of Nd up to minus of xp. So if our abrupt junction approximation holds good, then we can directly calculate the electric field during this charge density. What is that? We can easily obtain it from Poisson's equation, which is nothing but rho by epsilon s, which is the permittivity of the semiconductor material itself. Es means epsilon s is nothing but the permittivity of the semiconductor. So del of E, that means gradient of E from the Poisson's equation. So up to this, it is clear to you? So we can write it in a different way, just del Ex E of x. And again, we know Ex, electric field is nothing but negative differential of potential. So d dx of phi x. Yes, phi x is the electric potential. Now this equation can be, so this is equation number 1, this is equation number 2, and probably now we can plug equation 2 into 1. So we have rho x by epsilon s is equal to del Ex is equal to del square. So we will have a minus over here, del square pi x del x square. So this is equation number 3. Now rho x, we already have that quantification of rho x. What is that? Rho x is equal to minus E of E dot Na, E times Na, for the depletion region with extending up to xp and greater than 0, E of minus Na. Do you agree with this? We have already written, we have already drawn this here also. This profile has been drawn here. And rho x, so rho nx and rho px. Rho ax, rho nx. So this convention is okay with me. So E Nd 0x up to plus of xn. Do you agree with these two equations? Yes?
Now what is Na?
What is?
Na. After the third equation. Rho of x
The
Na.
E of Na. So this is Na actually. This is Na.
What is Na?
Na is the. কে বলেছো? What is Na?
Ma'am, what is Na? Like if Na is
কে বলছো?
Ma'am, I'm non-Bengali. I can't understand Bengali. Sorry.
Who is speaking about Na?
Ma'am, me. Mohsin.
So Na is nothing but the acceptor impurity concentration. Acceptor impurity concentration that is on the P side. That is Na. Because you are being doping the P side with the acceptor impurities. So Na specifically tells how much of this are ionized.
I forgot that. I already have written that. Sorry.
Yes.
Something else.
Please do study in your home also. because Na and Nd, these notations has been given from the very first of your
Thermal,
classes.
in the thermal equation of concentration of Boltzmann.
Yes.
ma'am.
So this is the scenario. Now to calculate the electric field, we will just integrate this. So integrating this equation, we will have an expression for Ex. So do that very fast. So integrating equation 3, what we are having with rho x by epsilon s is equal to Ex dx, and we are having del Ex rho x Ex dx, and this is nothing but Ex is equal to minus ENA by epsilon s into x plus constant of integration, that is C1. This is equation number 4. Do you agree up to this? Now in the neutral P region, as we have already said that in the P region where we are going to the bulk side, where if we go to the bulk of the P region, that means where is the no space charge region, that means the P region where there are plenty amount of holes and acceptorants are there on the P side, and on the N side there are ample amount of donor impurity atoms as well as associated electrons with it. Beyond the space charge region, what is expected? To find this constant for integration, we will put some of this to 0. That means Ex to be 0. Do you agree with this? That means the E should be 0, as because the charge neutrality condition is maintained in the bulk site. So at the junction itself, E is equal to 0. And this is E is equal to 0. In the bulk semiconductor. So putting this right over here, that is E is equal to 0, at putting this condition x less than or equals to xp, that means on the side where the space charge region is not there, on the side that is equal to and less than that of the space charge the extension on the p side, space charge extension on the p side, beyond that extension, what is that? C1 we can easily calculate here it from here, putting this condition onto equation number 4. We'll plug onto this condition and what we are left with is C1 is equal to 0 minus ENA divided by epsilon s, yes, minus of xp. Am I correct? My derivation is correct or not? Therefore, at P region, the electric field at P region is equal to, putting this constant onto this equation, that is equation number 4, we will obtain minus E Na epsilon s x minus E Na epsilon s x p. E Na epsilon s x plus xp, and this condition particularly holds for xp x less than or equals to xp greater than or equals to 0. Similarly, for the n region, what we are left with, for the n region, I'm directly plugged. Okay, I'll just derive it. At n region, E is equal to END divided by epsilon s x plus C2. Similarly, C2 is the constant for integration at x greater than or equals to n. E is equal to what? E is equal to 0. Do you agree with this? In this case also.
Yes, ma'am.
Okay. So at x greater than or equals to xn, E is equal to 0. Now we can plug onto this condition onto this equation, that is equation number 6. If that one is the equation number 5, and we plug onto this condition onto this equation number 6. So we will have 0 is equal to E times nd epsilon s xn plus C2, and C2 is nothing but minus END divided by epsilon s into xn. Putting this value of C2 onto 6, we will finally obtain the electric field at the n region, which is nothing but minus END divided by epsilon s xn minus x. So here are the two equations, that is equation number 5 and equation number 7. Now there is further, there are several levels of layers of approximation. If you keenly notice onto these derivations, what we have yet derived, there are several layers of approximation that we are taking into account. So the first approximation, maybe probably we have directly applied the abrupt junction. We have actually applied an abrupt junction approximation, but in the actual scenario, such abrupt junction may not be happening because of several design issues. So that was the first layer of approximation. Then what we have told, if our temperature is above 0 and much above 0 kT, much above 0 K, then we can apply Boltzmann approximation. That is second. There are several layers of approximation that will be taken into account to derive what we want to derive, because this basically eases our calculation in the counterpart. So now, yes.
Why are we taking E and xn equals to 0?
Yes.
Ma'am, why we are taking E at xn and x equals to 0?
I can't listen you actually, Shomojit. Please a little bit louder.
Ma'am, I am asking that why we are assuming that E at and xp at 0.
Why? Let me repeat your question. I can't get you actually. Why E is 0 at x greater than xn?
Yes, ma'am.
E
Greater equal to ma'am xn.
Yes, কারণ ওখান থেকে আমার abrupt junctionটা শুরু হচ্ছে at x equals to xn, that must not hold good, because ওখান থেকে আমার next junction মানে we are basically moving on to the bulk region. So at that particular boundary condition, this at less than xn or onto the p side less than p xn, that should not happen actually. The electric field should be 0.
ম্যাম তবে এই যে E এর যে ফাংশনটা এলো ওটা তো তবে লেস দেন xn এর জন্য মানে
কোনটা?
আচ্ছা ঠিক আছে ম্যাম, ঠিক আছে 0 হচ্ছে, ঠিক আছে।
Okay, তাহলে একটা now again if we assume that the electric field is continuous at the meteorological, again one thing is to remember that এই যে meteorological junction এ এই যে দুটো আলাদা আলাদা ভাবে আমরা ইলেকট্রিক ফিল্ড জেনারেট করেছি, মানে ইলেকট্রিক ফিল্ড at the end region, electric field at the P region, এই metallurgical junctionটাই কিন্তু continuous হতে হবে, just at the junction, just right at the x is equal to 0. এই জাংশনে কিন্তু that should be continuous, and for that we should have such condition that this electric field on the end region, particularly at x equals to 0, that should be equal. So moving on to this thing, we will have, if we can equate this to things, then what we'll have been left with is minus ENA epsilon s x plus xp is equal to minus END divided by epsilon x xn minus x, and এটাকে যদি আমরা একটু সিম্পলিফাই করে নেই, x minus ENA epsilon x dot xp is equal to minus END by epsilon s xn plus END divided by epsilon s into x at is equals to 0. Therefore, at x equals to 0, what we are left with? Minus E, just put x equal to 0 throughout this equation, E into Na by epsilon s x.
When the ratio of doping and the depletion region becomes equal.
Yes, exactly. So divided by epsilon s, and that particularly boils down to Na dot xp is equal to Nd dot xn. Thus, the number of the negative charges per unit area in the P region is equal to the number of positive charges per unit area in the N region. So we have started off with the, তাহলে কি হলো, আমরা রো মানে যেটা চার্জ ডেন্সিটি থেকে আমরা শুরু করেছিলাম সেখান থেকে আমরা ইলেকট্রিক ফিল্ড পাচ্ছি জাস্ট বাই ইন্টিগ্রেটিং। তাহলে আমরা যদি রোর প্রোফাইলটাকে ধরে নিই, সেটাকে ইন্টিগ্রেট করলে কিরকম হবে? একটা লিনিয়ার ফাংশন হবে, তাই তো? আমরা যদি রোটাকে যেরকম প্রোফাইল আমরা এঁকেছি দুটো স্কোয়ার বক্স, সেই দুটোকে যদি ইন্টিগ্রেট করি, তাহলে আমাদের ইলেকট্রিক ফিল্ড কিরকম আসার কথা? a linear with an angle of 45 degree, তাই তো? If I am not wrong. Okay, তাহলে potential কিভাবে পাবো? Just by integrating this electric field, তাই তো? তাহলে এই লিনিয়ার ফাংশন যেটা এখন পাবো, মানে যে প্রোফাইলটা আমি এক্ষুনি ড্র করব ফর ইলেকট্রিক ফিল্ড, পোটেনশিয়াল ফাংশন হবে জাস্ট এর লিনিয়ারের ইন্টিগ্রেশন করলে কি হয়, আমরা কোয়াড্রেটিক পাই। তাহলে পোটেনশিয়ালটা জাস্ট একটা কোয়াড্রেটিক ফাংশন হবে। Is it expected or is it clear to you? So just try to draw it. মানে আমি পোটেনশিয়াল ফাংশনটা এখনই ধরতে চাচ্ছি না, ওটা একটা
Can you please repeat once?
yes.
Can you please repeat again?
No, we have basically started off the whole process by considering that this is a step graded junction. Step graded junction, that means where the profile ends abruptly just when a new profile begins. So in that case, we have drawn our charge profile, charge density volume, charge volume density, where we have seen two square boxes, one in the negative direction and one in the positive direction, these two profiles. And if we can think of logically, if we try to integrate these two things, then we will have a linear function at an angle of 45 degrees. So let us try to draw that. মানে এটা তোমরা নিজেরা মেবি তোমরা ইকুয়েশন সলভ করে করতেই পারো, কিন্তু বুঝতেই পারছো যে ইলেকট্রিক ফিল্ড যখন তুমি ইন্টিগ্রেশন করে রো এক্স কে ইন্টিগ্রেশন করে পাচ্ছো, দ্যাট মাস্ট বি এ লিনিয়ার ফাংশন। এরপরে তুমি পয়েন্ট প্লট করে দেখতেই পারো, দ্যাট ইজ নট অ্যান ইস্যু। বাট intuitively what we can draw is, if this is your electric field and this is the region where xp and this is your region where there is an xn, then in this p region and up to this in the end region. Okay. So this is the profile for the electric field. Now we will be heading towards the calculating and deducing the nature of the potential function. So I think I shouldn't start today, actually, because that part is also huge. That will কারণ তোমাদের ল্যাবটা আছে, না থাকলে হয়তো যেত in that case. So up to this, is there any doubt?
No, ma'am.
Okay. আমি ডেরিভেশনস গুলো কিছু কিছু করাচ্ছি, বাট মোর ইন্টারপ্রিটেশন, মানে তোমরা ইন্টারপ্রিটেশনটা বুঝতে পারছো কিনা, তাহলে একটা জিনিস আমরা এখান থেকে পরিষ্কার বুঝতে পারছি যে খুব সিম্পল, যখনই দুটো পিএন জাংশন আমরা জয়েন করতে পারলাম সেই মুহূর্তেই কি হচ্ছে, ডিফিউশন ইজ অন। ডু ইউ এগ্রি উইথ মি?
Yes, ma'am.
When there is some when two different layers of semiconductors are being joined, the diffusion is on. This random movement of flow is there when you increase the temperature to a little bit. তাহলে কি হলো, এই যে ডিফিউশন শুরু হওয়ার জন্য যে প্রসেসটা আমার স্টার্ট হলো, এই যে ডিফিউশন প্রসেসটা স্টার্ট হলো, এটা তো কন্টিনিউয়াসলি চলতে পারে না, এটাকে থেমে যেতে হবে কোথাও। আর সেটা কে ডিসাইড করবে? সেটা ডিসাইড করবে হচ্ছে আমার মধ্যের ইলেকট্রিক ফিল্ড, যেটা তৈরি হচ্ছে এই আনকভার্ড চার্জেস। দ্যাট মিনস পজিটিভ চার্জেস অন দ্য এন সাইড অ্যান্ড দ্য নেগেটিভ চার্জেস অন দ্য পি সাইড। ইমোবাইল আয়ন্স যেগুলো রয়েছে, আনকভার্ড ইমোবাইল আয়ন্স যেগুলো রয়েছে, সেগুলো ডিসাইড করবে আমার কতটা ইলেকট্রিক ফিল্ড জেনারেট হয়েছে। ইজ দ্যাট সাফিসিয়েন্ট টু স্টপ দ্য ডিফিউশন কারেন্ট অর নট সো? তাহলে ততক্ষণ সেটা ইনক্রিজ হতে থাকছে। ইজ ইট ক্লিয়ার? সহজ বাংলায় আমি যদি পুরো ব্যাপারটাকে ডেসক্রাইব করি, তাহলে এটা কতক্ষণ চলবে, এই যে ফ্লো অন প্রসেসটা, কভারিং দ্য জাংশনস, ক্রসিং দ্য জাংশনস, গোয়িং অন টু দ্য রিকম্বিনেশন প্রসেস, এটা কতক্ষণ চলবে? যতক্ষণ এই সাফিসিয়েন্ট অ্যামাউন্ট অফ এই বিল্ট ইন পোটেনশিয়াল ভোল্টেজ বা বিল্ট ইন ভোল্টেজ, দ্যাট ইজ দ্য প্রপার্টি অফ দ্য মেটেরিয়াল ইটসেলফ, যতক্ষণ না এস্টাবলিশড হবে ততক্ষণ আমার এই প্রসেসটা কন্টিনিউ করছে। থেমে যাবে কখন? যখন আমার এই বিল্ট ইন পোটেনশিয়াল ভোল্টেজ, এই ব্যারিয়ার পোটেনশিয়ালটা এনাফ যে ওরা বলবে না এবার তোমরা জায়গায় ফিরে যাও, আর নেই, এখানে জায়গা নেই, এখানে অনেকটা বেশি উঁচু, তোমরা এটা কভার করতে পারবে না। অনলি সাম ভেরি হট ইলেকট্রনস, অনলি ভেরি ফিউ হট ইলেকট্রনস that find its way to cross over to the junction, then can take part into this recombination process. Kintu generally speaking, most of the electrons thereby stop going and crossing the junction. এই জায়গাটা ক্লিয়ার হয়েছে? তাহলে আমাদের কি হলো, এর বেশি কিন্তু আমরা একটা জাস্ট পিএন জাংশন জয়েন করে এগোতে পারছি না। তাহলে এবার আমরা কি করব? we will go on putting some biasing arrangements. ওকে, এবার আমরা বায়াসে, আমি কেন এটা বলছি, কারণ আজকে তোমাদের এটা নিয়ে ল্যাব আছে, সেই জন্য একটুখানি জাস্ট একটু ইন্ট্রোডাকশন পার্ট। কেন বায়াসিং অ্যারেঞ্জমেন্ট করব? জাস্ট টু রিডিউস দিস পোটেনশিয়াল ব্যারিয়ার। না, আমি ব্যারিয়ারে পোটেনশিয়ালটা কমাতে হবে, আদারওয়াইজ দ্য ইলেকট্রনস ক্যান নট ক্রস টু দ্য পি সাইড অ্যান্ড হোলস ক্যান নট ক্রস টু দ্য এন সাইড। পোটেনশিয়ালটা কমানো, এবং সো ইনটুইটিভলি যেটা আমরা এক্সপেক্ট করি যে এই যে ইলেকট্রিক ফিল্ড যে ডিরেকশনে এখন তৈরি হয়েছে ডিউ টু দিস আনকভার চার্জেস, আমার পোটেনশিয়ালটা এমন ভাবে দিতে হবে, দেন দ্য মাই ডিরেকশন অফ দ্য পোটেনশিয়াল that is externally supplied to this piece of semiconductor should be what? এই যে ডিরেকশনটা, সেটা এই যে ইনবর্ন যে পোটেনশিয়ালটা ডেভেলপ হয়েছে সেটার অপোজিটে হতে হবে। ওকে, তাহলে আমার বায়াসিং অ্যারেঞ্জমেন্ট আমাকে ফ্যাসিলিটেট করবে এই প্রসেসটাতে, যাতে আমার এই যে জেনারেটেড বা ইনবর্ন যে পোটেনশিয়াল, বিল্ট ইন পোটেনশিয়াল ব্যারিয়ারকে ও যাতে বেসিক্যালি ওটাকে কমায়। and there is some minus effect of this externally applied voltage. এটা হচ্ছে ফরওয়ার্ড বায়াস। ফরওয়ার্ড বায়াস means connecting the p side to the most positive terminal of the battery and connecting the inside to most negative terminal of the battery. This is that. কিন্তু এটার জন্য কি হবে, আমার যে ইলেকট্রিক ফিল্ডে এক্সটার্নালি অ্যাপ্লাইড ইলেকট্রিক ফিল্ডটা জেনারেট ডিউরেশনটা হবে, দ্যাট উইল বি অপোজিট, দ্যাট উইল বি হিন্ডারিং দিস ইলেকট্রিক ফিল্ড দ্যাট ইজ জেনারেটেড বিল্ট ইন। তাহলে কি করবে, এই প্রসেসটা বেসিক্যালি ফ্লোকে জেনারেট করবে, মানে দিস যেহেতু ব্যারিয়ার পোটেনশিয়ালটা এখন লো হচ্ছে, তার জন্য কি হবে, নাও ইজিলি দিস হোলস can cross to the inside and easily these electrons can cross over to the p side. So if we can draw it like this, then p and n, already there is some immobile acceptor ions which are present over there, and on account of this E is there. Now what we are saying is that we will apply a forward bias voltage whereby p side will be connected to the most positive terminal of the battery and inside to the most negative terminal of the battery, and you can see here that the direction of the electric field in this way. So that basically cancels out this electric the bit lower. It basically lowers this built-in potential barrier, so to facilitate the process of flow of the electrons and holes and crossing the either side of the junction. What happens now if we connect this p side to most negative terminal of the battery and n side to the positive terminal of the battery? What is the arrowhead points to? In this direction? Do you agree with me?
Yes, ma'am.
Same direction of the internal.
Yes, that will be in total sync with the direction of the built-in electric field, which basically hinders this process of on account of which this barrier potential or the depletion width will increase, and there are so on and so forth things will be happening over there that we'll discuss. But up to this, you just try to understand this, that with this effect, with this increase in the reverse bias, what will happen, this depletion region width will start to increase, and the electrons and the holes on either side of the junction will see a large potential barrier in front of them. So neither of these two charge carriers can cross the junction. তার জন্য কি হবে, in this reverse bias direction a very little current is observed, কিন্তু ফরওয়ার্ড ডিরেকশনে মানে ফরওয়ার্ড বায়াসে আমরা বেশ সিগনিফিকেন্ট অ্যামাউন্ট অফ একটা কারেন্ট পাই, যেটা আমরা প্লটও করতে পারি কার্ভে, মানে forward bias voltage, forward current with respect to the forward voltage. So that is significant. But this reverse voltage and the reverse saturation current is very low. So we will have experiment on both of these characteristics. But যেটা হচ্ছে নরমালি এই built-in potential barrier for different materials are different. Okay, do you know that? For silicon it is 0.6 to 0.7 volt. Okay, for germanium it is more or less probably 0.3 to 0.35 volts. Okay, so at room temperature the voltage across the depletion layer for silicon is nearly 0.6 to 0.7 volt. So what does this mean? So you have a p-n junction diode in your hand. So if you have a silicon diode in your hand, and what do you expect? What do you expect for getting what do you expect, or what actually you have to do for getting a significant amount of forward bias current? Yes,
To apply a potential which would be greater than 0.7.
yes, but what is that? Please repeat.
You have to add a battery whose potential must be greater than the 0.7 electron
We
volt.
must supply an energy or voltage that is greater than 0.7 volt. So any observable current will be above 0.7 volt. If it is if its potential barrier voltage is 0.7 volt. So when this PN junctions are formed, when this junction is formed, this built-in potential value comes hand in hand. Normally that is written in the diode itself, or maybe it is known to you. For germanium diode, you have seen a germanium diode, you have seen a silicon diode, and all of this for all of these devices, the measurable amount of current is observed only when you cross this built-in potential barrier voltage. Yes, is it clear to you? তাহলে
Yes,
সিলিকন
ma'am.
ডায়োডের ক্ষেত্রে এক্সপেরিমেন্ট করার সময় আমি 0.7 অবধি হয়তো কোনো কারেন্ট দেখতেই পাবো না, ক্লোজ টু জিরো। কারণ তখন আমি কি ভাবছি, মানে যেহেতু ব্যারিয়ার পোটেনশিয়ালটা অলরেডি তৈরি হয়ে রয়েছে, ডায়োড তৈরি হওয়ার সাথে সাথে এটা তৈরি হয়ে রয়েছে, সেজন্য আমি যতক্ষণ না তার উপরে বাড়াবো আমার তো পোটেনশিয়াল ব্যারিয়ারটা কমছে না। যখন অনলি পোটেনশিয়াল ব্যারিয়ার জাস্ট রিচেস 0.7 বা গ্রেটার বা এক্সটার্নালি অ্যাপ্লাইড ভোল্টেজ যখন গ্রেটার দ্যান 0.7, তখন কি করছে, আমি একটু একটু করে দেখতে পাবো যে আমার কারেন্টটা ইনক্রিজ করছে। হ্যাঁ, মানে ততক্ষণ অবধি আমি একটা নেগলিজেবল অ্যামাউন্ট অফ কারেন্ট বা কাছাকাছি জিরোর কাছাকাছি একটা কারেন্ট দেখতে পাবো, যেটা তুমি তখন হয়তো ভাবতে পারো যে এখনো কারেন্ট পাচ্ছি না, but that is not true, because this is the barrier potential which basically now restricting it from the flow of currents, since you although you have supplied an externally applied voltage, still you are not getting any current because of this built-in potential barrier. Is it clear? তাহলে যখন তুমি ধীরে ধীরে for silicon diode, when it increasing beyond 0.7, you will start getting some amount of current after that. Okay. So there are also other phenomena which might occur, because there are also experiments with the reverse bias. This is the case of the forward bias, and what I have told is that you will expect a larger amount of current after 0.7. But also in the reverse bias case, there are some phenomena that are happening over there. এটা এক্সপেরিমেন্ট করার সময় দেখবে যে কিছু 10-12 ভোল্ট অব্দি তুমি কোনো কারেন্টই পাচ্ছ না, কিন্তু রিভার্স বায়াসে 10-12 পরেই হঠাৎ একটা there is a severe increase in the ব্রেকডাউন ফেনোমেনা তৈরি হচ্ছে, এবং এই ব্রেকডাউন ফেনোমেনা গুলো আমরা আস্তে আস্তে আসবো। বাট বিফোর দ্যাট, যদি আজকের আমি দুটো করাতে পারি তাহলে করাবো দুটো, বাট দুটো নাও হতে পারে, ওই বলতে বলতে হয়তো টাইম পেরিয়ে যেতে পারে। কিন্তু এই ফরওয়ার্ড বায়াসের বেসিক্যালি পারপাসটা হচ্ছে এখানেই যে আমি একটা কারেন্ট দেখতে চাচ্ছি যেটা তো আমার পোটেনশিয়াল ব্যারিয়ারটা সার্কামভেন্ট না করলে পাবো না। সো দ্যাট ইজ ওয়াই উই আর অ্যাপ্লাইং ফরওয়ার্ড ভোল্টেজ। তাহলে আমরা আজকের আমাদের যে ল্যাবের পোর্শনটাতে সেখানে আমরা মেইনলি খেয়াল করব ফরওয়ার্ড বায়াস কারেন্ট উইথ রেসপেক্ট টু ফরওয়ার্ড বায়াস ভোল্টেজ। ওকে, সেটাই আমরা প্লট করব, and henceforth we will justify all those findings. ওকে, আজকের যেটা হচ্ছে, তোমরা তো প্রত্যেকেই জয়েন করছো, তাই তো? আর তোমরা কালকের সেশনটাতেও জয়েন করবে যাদের ডাউট থাকবে, কারণ আজকেই আমি তোমাদের এই ভিডিওগুলো পাঠিয়ে দেব, ওই মানে যেটা ল্যাবের ভিডিওগুলো পাঠিয়ে দেব। যদি কালকে কোনো প্রবলেম থাকে, আমাদের কালকের দিনটাও রয়েছে, মানে তোমাদের যেহেতু দুদিন ল্যাব। ওকে, I think most of you have you know this thing. Okay, আজকে তো সবাই তোমরা তো সবাই আসছো আজকের মানে 2:30টার সময়, তাই তো?
Yes, ma'am.
ওকে, তাহলে তোমরা আজকে যেটা ভিডিওটা দেখানো হবে সেটা সবার জন্যই হচ্ছে, আর কালকে যদি কোনো কোয়েশ্চেনিং সেশন থাকে বা কিছু থাকে সেটা কালকের হবে। ওকে, আর প্রবাবলি আমি হয়তো বুধবারের ক্লাসটা নেব না, আমার ইউনিভার্সিটিতে একটা কনফারেন্স আছে, আমি তার বদলে শুক্রবার তোমাদের ক্লাস নেব। ওকে, দিস অ্যানাউন্সমেন্টস এন্ড ওকে, তাহলে আজকের জন্য আমি লেট অফ করছি। আমি
ম্যাম ফার্স্ট অ্যাসাইনমেন্টটা কবে সাবমিট করব সবাই?
সে তো সাবমিট করে দেওয়ার কথা আজকেই।
ম্যাম অনেকজন আমরা ওই ট্রানজিস্টর আর আইসি লিখিনি, তো ওটা আবার কি লিখতে হবে?
হ্যাঁ, লিখতে হবে তো, যেগুলো দেখানো হচ্ছে সেগুলোই তো।
কালকে লাস্ট ডেট হতে পারে, তাহলে আজকে শেষ করে নেবো।
হ্যাঁ, কালকে লাস্ট ডেট, মানে তোমরা তো শুধু শুধু এক্সটেন্ড করছো আর কি, আর কি বলবো। সে তোমাদের প্রথম
ম্যাম,
দিনই বলা হলো তো না
না
যে
ম্যাম, কমপ্লিট হয়ে গেছে। আমরা আসলে কজন ট্রানজিস্টার লিখিনি, তো আবার লিখতে হবে, সেই জন্য বলছিলাম।
ঠিক আছে, লিখে নাও, লিখে কমপ্লিট করে জমা দাও
কোথায়
আর ম্যাম
সাবমিট করবো ম্যাম?
ক্লাসরুমে।
ঠিক আছে।
ওকে।
ম্যাম ওই সুইচ, অ্যামমিটার, ভোল্টমিটার এগুলো লিখতে হবে?
না, সুইচ অ্যামমিটার ভোল্টমিটার লেখার দরকার নেই।
ওকে।
ওকে,
ম্যাম এই
ঠিক আছে।
লিঙ্কটা থেকে বেরিয়ে যাবো তো? নাকি এটা
লিঙ্ক থেকে বেরোনোর দরকার নেই। ওকে, লিঙ্ক থেকে বেরোনোর দরকার নেই, মানে আমিও বেরোচ্ছি না লিঙ্ক থেকে, লিঙ্কে আছি। এই লিঙ্কেই আবার সবাই জয়েন করবে। ওকে,
ওকে।
মিউট করে চলে যাও, এসে জয়েন করবে, আর 8 ঘন্টা তো রয়েছে।